All right, folks. This is the play pause it on top lock slipping or not. And I think I'm just going to put all the content in one long video because it's all connected. All right, so listen to whatever speed you want. Take a pause if you need to. But I chose some pictures for the type of problem you might see. So the classic simplest problem is two blocks on, one block on top of each other with an external force, and they might move together as a system or not. This is the problem we're going to go through. Other problems I have seen on the AP are, instead of this 30 Newton external force, the force driving the whole system is caused by the weight of something hanging over a pulley. I also found one on a website with answers, and that's posted in the second assignment in the module, where the external force was crooked. So, but I found a whole bunch of online videos with solutions. So hopefully after a while you'll see that it's the same kind of idea over and over again. So let's go ahead and get started. All right, problem type number one, a little bit easier. We're going to deal with the situation when the block is not slipping. All right, so if they are not slipping, then they have the same acceleration, and we only have to find that one value. So this is a great review of connected objects and systems. You can basically, depending on what the question is asking, treat this as one solid 12 kilogram object. But let's practice that. Let's draw the forces on the system, and then we'll use that to calculate the acceleration of the system. Okay, so we're gonna draw the internal and the external forces as a good review. Okay, so they drew the 60 Newton force. Both objects have weight, and I would encourage you to label that. You have to. There's not a choice. You need them separate, and we'll see why. So we have M1G and M2G. The Earth is pulling on each of these separately. A mechanical is at maybe 60 newtons. Okay, the normal force, that's tricky. That's one reason we're doing this separately. So let's look at each block. How many surfaces is the 8 kilogram block touching? It's touching the floor, so you've got the force of the normal. I'm going to call this F normal floor. And it's touching this surface from the 4 kilogram. So those electron clouds push down, and that I'm going to call F normal block. But we just dealt with the 8 kilogram. So let's look at the 4 kilogram. How many surfaces is the 4 kilogram touching? Just one. And by Newton's third law, I'm labeling these both F normal block. They're not the same vector because they have opposite direction, but I'm just labeling the magnitude next to the vector, and the arrow is indicating the direction. So these two are action-reaction pairs. That's your internal force. Okay, and so later on we're going to separate each block because internal normals, as you know, are pretty hard to visualize. Okay, there's no rope, so we can throw out the tension. All right, friction is really, really tricky. And again, that's why this is separate AP level problem. All right, so anytime you have a normal, you also have the potential for friction, right? Because friction equals mu times the normal. And you want to think about what the surfaces would do without friction. So the 8 kilogram, let's deal with the easy one. You've got this normal force that is causing kinetic friction between the 8 kilogram block and the table. Those nooks and crannies are bumping over each other. All right, and then remember the frog across the carrying across the room demo, it's kind of tricky. What would this 4 kilogram object do if there were no friction? You can imagine that has inertia, that wants to just stay in place. So if you could imagine like pulling the tablecloth out from under the dishes, the 4 is going to stay in place and the 8 kilogram block is going to slide out from under it. I'll try to make a video, like a real life video, and then add that at the end. So relative to the block below it, or let's do it this way. You can imagine the nooks and crannies of the thing below it sticking up like that, and the nooks and crannies of the 4 doing this, right? So from the perspective of the pink object, the blue nooks and crannies are pushing back, right? The pink nooks and crannies are trying to go to the right, and the blue nooks and crannies are in the way. So there is, but they're interlocking. They are not sliding. So on the pink block, there is the blue nooks and crannies are pushing this way, and that's static friction. But from the point of view of the blue block, you can imagine yourself sitting on the metro train or bus, and you're just sitting there trying to be at rest, and the pink nooks and crannies are propelling you forward because they're moving and you're in the way. So there is a, should have drawn this bigger, there is a action-reaction pair of static friction. So that's what we have. This is what we haven't seen before. Static friction is an internal force. So we've seen internal normals, but we haven't seen static friction as internal forces. Okay, that's kind of tricky, but just visualize those nooks and crannies. The pink ones are pushing the blue to the right. That's this force. The blue ones are pushing the pink to the left. That's this force, and they cancel. Okay, so that is super complicated, and we're gonna, if you're still like puzzling about that, we're gonna separate out all the forces on each individual block separately in a minute, and hopefully that'll help. But those are all the forces, internal and external. Okay, and then we're going to calculate the acceleration of the system, which is the sum of the external and forces that are parallel to the motion over the sum of the masses. Okay, so the 60 newtons is, and remember, with the acceleration is positive and opposite the acceleration is negative. So the 60 newton is coming from outside the system. We don't know what that is, person, whatever, minus and we're just focusing on the horizontal forces. So that static friction keeping the two blocks together is internal as long as they're not slipping. So we love that. Those two are canceling. We don't have to worry about it. We don't have to worry about any of the up and down forces. So it's just 60 newtons minus the nooks and crannies from the table, because the table's not part of the system. And that's kinetic friction over 8 plus 4, or 12 kilograms. Okay, so that's the acceleration of the system, but oops, we got to go to our miscellaneous column and calculate the force of friction, which is mu, which we have, times the normal, which normal? The normal at that surface, which is this, I guess, red, orange, F, normal F. And then you're like, okay, I got to find that force, so I actually do care about the perpendicular forces. So we are going to, hang on, we'll do this, I'll erase. Okay, so that's why I love the columns, is because when you get stuck, you can be like, oh, what have I not dealt with? All right, so we get stuck in the miscellaneous column, we need to find friction, so we're going to go to the vertical column and say the system is not accelerating vertically. I have this positive normal force from the floor, which is what I want, and I have minus the weight of the top block minus the weight of the bottom block. Oops, I guess I called that one M1 and that M2, but anyway, you know what I mean. And that equals 0. Okay, and then 4 times 9.8 is 39.2. Oh, sorry, that's M2. And 8 times 9.8 is 78.4. So the pressure or the normal on the floor is 117.6 newtons. Okay, it's just the weight of both blocks, but I really want you to see where that comes from, and I think it's really important to label this separately, as annoying as that might be. Okay, now we can go back to our miscellaneous column, calculate friction, and that's 0.01 times 0.10 times 117.6, or 11.76 newtons. Okay, now we can go back to our what we really care about. The acceleration is going to be 60 minus 11.76. That's awesome. That means it's going to be moving because 60 is bigger than that. And when you work through the math, you get an acceleration of 4.02 meters per second squared. All right. So far, other than the force diagram, hopefully this all makes sense, right? The normal is really just the weight of both, not a surprise. And I have two outside forces. Okay. And it's not powered by gravity, so it doesn't have to be less than 9.8, but that's your acceleration. Now keep that number. Hopefully you're taking notes, good notes, but keep that number. We're going to need it. Okay, so we are done with this slide. Now we're going to focus on just the top block. And we need to know how strong those nooks and crannies need to be for it not to slide. This is a classic problem, right? Those nooks and crannies are going to be stressed, and at some point they're going to give out. So we need to make sure that we have enough static friction. Okay, so again, we can, if that force diagram was confusing, we'll practice one more time. Okay, so let's isolate the 4 kilogram, and let's use our we must never forget this. Okay, so we have the weight, which is 39.2. We have the normal from the block below it. Did I put that on the other one? Yeah, I had to pink it. Okay, so we have how many surfaces is it touching? It is touching one surface, and those electron clouds say, hate you. These two are equal because it's not accelerating up and down. So this is a boring problem. This normal force is equal to 39.2. Okay, we don't have to show our work for that. But then this is what is tricky. So again, this block is trying to stay at rest. So I'll draw this one more time more slowly. So this block has nooks and crannies, and it is trying to just sit there. And the block below it has nooks and crannies, and it is moving. So you can see that each of those little nooks is pushing to the right on the 4 kilogram block. So we have a force of friction, which is static, acting to the right on the 4 kilogram block, which makes sense because it's accelerating to the right with a value at 4.02 meters per second squared. So it needs, sorry, that's sloppy. It's got to have a rightward force, right? So again, it's coming from the nooks and crannies. That is very hard to visualize because it's happening on such a small level. That's it. It's a simple force diagram, but what is really, really weird is that we tend to think of friction as slowing things down. And so your brain is going to be like, wait, how is friction speeding something up? But again, think about the nooks and crannies. Okay, so we drew all the forces on the top block. Now we're going to figure out what that mu here needs to be in order for the blocks to not slip. Okay, so it sounds really abstract and complicated, but if you were just given this force diagram, you can see that the force diagram itself, once you figure it out, is not super hard. Okay, but what is weird is that it is static friction that is moving that block forward. And static just means the nooks and crannies aren't bumping over each other. They're interlocking and pushing. The other thing you want to be careful about is when you're looking at a single object, we're only looking at its mass versus when you're looking at the whole system. But they both have the same acceleration. That's why it's a system. Okay, so the static friction force, those nooks and crannies have to hold on with this much force. So we're looking for mu s. We looked for, because it's a boring problem, the normal force is, I'm not showing enough work, sorry, on the AP you should say F static equals mu n somewhere, right? F static equals mu n. And this is 16.08, right? And so if you solve for mu, you get mu equals 0.410, which it's a made up problem, but yay. It makes sense because it's physically possible because it's less than 1. Okay, so mu could be bigger than that. That's the minimum it needs to be. If it's bigger than that, it means the nooks and crannies are holding on and they're not even close to giving out. Okay, so that's what mu needs to be. Again, this is a classic problem. Okay, and then we want to find all the action-reaction pairs for every force in the system. This has shown up every once in a while, so a good practice with Newton's third law. And okay, so let's just get started and use our we must never forget this and do one at a time. All right, so the 8 kilogram has a weight equal to 78.4. Flip the nouns. This is Earth attracts the 8 kilogram with 78.4 newtons. So the reaction to that is that the Earth is being pulled upwards with a force of 78.4 newtons. Okay, so you have to draw the Earth somewhere and say that's the reaction to this force. These two are action-reaction pairs. All right, similarly, the 4 kilogram object is being pulled towards the Earth with a force of 39.2 newtons. Therefore, the Earth is being pulled up towards the 4 kilogram with a force of 39.2 newtons. These are action-reaction pairs. Okay, and there's a reason I'm asking you to do this. One, because it is an old AP problem, but two, for a reason that'll make sense. Sorry, getting ahead of myself. All right, let's do, okay, we did this mechanical, let's call the 60 Newton mechanical force. So the reaction force to that is if the person is pulling on the blocks with 60 newtons, then the blocks are pulling on the person with 60 newtons. So we don't know what's causing this, but whatever that is, that's the reaction force. Okay, the normal force, look at the 8 kilogram, you have the force of the normal from the floor or the table, I can't remember what I called it. That's pushing up on the 8 kilogram. So if you drew a separate force diagram for the table, you would have the force of the normal from the floor, table, whatever. These two are action-reaction pairs. Okay, and this is a normal force pressing down on the table. Do not call this the weight. Don't say this downward force is the weight of the two blocks. Remember, you can never measure your own weight, right? I could push down on the 4 kilogram block with my hand, causing this normal to increase. Okay, so the pressure at this surface, this force, is a normal force. It is caused by the electron clouds of the 8 hating the electron clouds of the table. Don't call it the weight. In this case, in magnitude, it is equal to the weight of both blocks, but do not label it weight. I'm making a big deal out of it because some of the AP solutions, if you find them online, have done that like once or twice, and it's wrong. Okay, so that's a reaction pair, and then even more importantly, what you're more likely to confuse is the 4 kilogram block has a, oops, I want this to be colorful, blue, has the force normal from the block below it, right? It has electron cloud saying, I hate you. The reaction to that is an equal and opposite downward force These two are action-reaction pairs. Similar to when we did the problems with two blocks touching each other like this, these two normals are action-reaction pairs. But because this is vertical, again, people are really, really tempted to call this weight. It is not weight. It is caused by the electrons of the 4 kilogram block pushing down. It is not caused by the Earth. Okay, this is the whole reason I wanted to do this one slide. Okay, I think we did all the normals. Yeah, so the 8 kilogram block has 2 normals. The 4 kilogram block has 1 normal. Friction is, the nooks and crannies are, I'm going to just call this F from the table, acting to the left on the 8 kilogram block. So what that means is they are acting to the right on the table. We just don't think about that because the table usually has enough other supports so that it doesn't move anywhere. Okay, but remember me on the paddleboard, it could move if, you know, if it were on a frictionless surface. Okay, so these two are action-reaction pairs, but that's acting on the table. That's why we didn't draw it before. Again, the really, really tricky one is, let's see what color we'll have, bright pink. Okay. The nooks and crannies are pushing, let's call this force of friction from the blocks. Static friction is pushing the 4 kilogram block to the right, like the Smart Butt frog demo. By Newton's third law, the nooks and crannies are pushing the 8 kilogram block to the left. Okay, these two forces are internal. So there's two ways of looking at this. When you find the acceleration of the system, you're going to divide by both. You're not going to include this because it cancels, but you're going to divide by the 4 and the 8 kilogram in the denominator because that's the inertia of your system. If you were to isolate just the 8 kilogram, then the reason this is moving more slowly is you would only include 8 kilograms of inertia, but you'd have 60 minus this friction from the table, minus the friction from the block above, and that would get you the same reduced acceleration of the 4.02 as opposed to whatever it would be 60 minus less friction over 8. Anyway, okay, so action-reaction pairs, kind of tricky. So pause, listen to this again if you need to. Okay, that is top block not slipping, and I will chapter this because we're already at 23 minutes. Okay, so wanted to make this all one video so you still had all the numbers on the page. Now we're going to say, all right, static friction is 0.24. That's not enough. It needed to be 0.41. So now we know they're slipping. So what's a little tricky is we're not talking about the force of static friction anymore. We're talking about the force of sliding friction, and sliding friction tends to be less. So I just, made up a number that was less. Okay. Now they don't have the same acceleration. So now we want to find the acceleration of each block. So we have two different accelerations. So we are going to just separate out the two blocks. So we're going to have A sub 4 and A sub 8. All right, I'm going to speed through the stuff we already know. This has a weight of 39.2. This has a normal force of 39.2. Even though it is turned into kinetic friction, it is still going to the right. Hopefully that makes sense. Let's quickly go back up here so we can draw. So now the nooks and crannies are bumping over each other. But so I think the best way to explain it is clearly these are still pushing it to the right. But what we're going to see is it's pushing it to the right, but we're going to see that the acceleration of the 4 is less than the acceleration of the 8, right? It has to be because it's slipping. So the 4 is going to continue to trail behind. So it's sliding backwards relative to the 8, but relative to a person on the side, it's still going forward, just not as quickly. That's what's really tricky, and that's what I'll try to make a video for you of it, like that demo in real life. So the pink nooks and crannies are still pushing on the purple nooks and crannies, but it's bumping them forward, but not as quickly as it's being pulled by the 60. All right, that's the best I can do in the video. Sorry if that doesn't make sense to you. All right, so the acceleration of the 4 kilogram block is the sum of all the external forces divided by its mass. Okay, and the only thing it has is the nooks and crannies. That's kind of weird. And it's kinetic friction, which is also kind of weird. We have not seen that before. And then you can go to your miscellaneous column if you want, or just say, okay, kinetic friction is mu times the normal over the mass. And this is 0.22, and the normal is 39.2, and the mass is 4 kilograms. So it is accelerating forward at 2.156 meters per second squared. Less than before, right? Because it had before it had, do we find friction? 11.7 newtons pushing it forward, and now we have, I don't know what that number is, but anyway, we reduced the force of friction. So it's accelerating less quickly to the right. Okay, so remember that number, 2.156. That's how fast it is going forward, being pushed by the nooks and crannies below it. Okay, and then this is what gets tricky, and then I'm going to do hints and warnings, so thanks for your patience. Okay, 8 kilogram. It has weight equal to 78.4. It has the normal force from the block above, but kind of transitive property, we already figured out the normal force from the block above, boring problem, was equal to its weight. So this is 39.2 newtons, which is why even the people posting the AP answers have labeled this, oh, this is the weight of the top block. It's not. It's the electron cloud pressure from the top block, which is equal to its weight. Okay, and then we have the force of the normal from the table. And let's pretend like we don't know that yet. And then we have we have kinetic friction with the table, and we have kinetic friction with the block. By Newton's third law, since this nooks and crannies were pushing 4 to the right, the nooks and crannies are pushing the 8 to the left. And the best way to explain this is if you imagine, a stack of 3 books, and I'm trying to pull out this blue book, like even like a sandwich. Pretend like I'm holding this in my hand. Pretend like I'm holding this together like a sandwich and squishing these together, and then a second person is trying to pull out the cheese I know that's disgusting, whatever. The cheese from the sandwich. You can see it's going to be resisted from both the top and the bottom. All right, so hopefully that makes sense. If not, come see me during office hours. Okay, so that's what's going on with the 8 kilogram block. That's more complicated than the top block. So if we want to find the acceleration of the 8 kilogram block, that is going to be the 60 newtons minus FK1 from the table minus friction from the block divided by, thank God the denominator's easier, 8 kilograms. Okay, so let's go into our miscellaneous column. Oh, actually, before we do that, let's go into the vertical column. And we need to find the normal. Again, it should, let's just, so sum of the forces is 0, the force of the normal from the table minus the normal from the block minus the weight equals 0. Okay, then that means the force of the normal from the table minus, okay, wait, that's what we're looking for, minus the 39.2 minus 78.4 equals 0. So we're going to get the same number that we got before, but not because it was equal to both weights. So before, when they were a system, it was force of the normal from the table minus the weights, because we were looking at them as a system and the normal was internal. It's confusing because it's the same number, but it's because the normal force and the weight of the top block happen to be equal because the top block's in equilibrium, right? So, okay, so the friction's going to be what it was before. Minus 0.1 times 117.6, because this normal, as long as the 4 kilograms stays on top, this orange normal is going to be 117.6, right? Because it has to support both blocks. Okay, so that all around the world to say that's the same, but I want you to see why, even though some things have changed. Okay, but we have this new force of friction. So that force of friction between the blocks, again, I'm trying to pull this blue block out from two different things, is equal to mu sliding. Oops. This is sliding. Times this normal, because that's the surface that we care about, which is 8.624 newtons. All over 8 kilograms. Okay, so I have an external force minus 2 sets of nooks and crannies that it's fighting against because it's sliding along 2 surfaces. And I got, hopefully this is right, 39.616 over 8, or 4.952 meters per second squared. Okay, so as a quick check, this is actually accelerating faster now than it was before because it's not having to carry the inertia of the 4. This is 4.952. What you absolutely need to check if you get a 2 blocks not slipping problem, or a slipping problem, is the top block's acceleration better be less than the bottom one, right? Because that's the whole point, is that the top block is falling behind because it's slipping. All right. Wish my handwriting was neater. That is top block slipping a classic. We're going to do some hints and warnings and then we're done. Okay, so just to check your work, the normal force on any object is equal to the weight of all of the objects above it. In general, I said usually, and I'll explain why in a second. So the normal force from the table is equal to the weight, if you got 4 blocks, is usually equal to just to the weight of everything above it. The normal force here would be the weight of everything above it. The normal force here would be the weight of everything above it. Okay, that's a quick way to just do a problem quickly if it's multiple choice and you don't get any credit for showing your work. The exception to that is I found a problem, so a good reason to go do it, of 2 blocks not sliding, but there was a crooked, it was a lawnmower problem. So it was a combination lawnmower block slipping problem. And you know, with lawnmower problems, that means it's no longer a boring problem and the normal is no longer equal to the weight. Okay, but just trust your math. Set up the sum of the forces vertically is equal to 0, and you can find what the normal is. Okay, but if you're doing just a quick If it's just a quick, easy problem, just each normal is the weight of everything above it. Okay, friction might be doing positive work. So one of the AP problems has you calculate the work done. Don't freak out if you find it doing positive work. So that top block, in both cases, it was the nooks and crannies that were propelling it forward. So that force is with the motion. That friction is doing positive work on the 4 kilogram block. It's doing negative work on the 8 kilogram block. It's, if you look at both of them together, it's a closed system, and it's just transferring the energy from the 8 to the 4. So it's taking away energy from the 8, giving it to the 4. All right, and this is the last slide. If the blocks are not slipping, the nooks and crannies are stressed, but they're keeping the blocks together, and this is static friction. So, if they give you both, sometimes they give you both, and you're only going to use one, and it's your job to know, oh, I'm going to use mu-s. If they are slipping, the nooks and crannies are bumping over each other, and this is sliding friction, so you look for UK. Okay, that was a long video. Thanks for your attention. But I found a whole bunch of good online problems. So, keep doing them until you say, okay, I got this. This is in some ways the same problem over and over again. All right, thank you for listening.